Hello all. So last class we looked at how to graph polynomials with our graphing calculator, and today we're going to focus on graphing polynomials by hand without our graphing calculator. So to help us understand how to graph polynomials, let's go over the general shapes of the graph of different types of polynomials. We know that polynomial functions are always continuous with rounded terms, which means that we should be able to trace our function, or polynomial functions, from the left to the right without having to lift your pencil. So it's continuous. And if there are turns, it's always rounded turns, so it's always curved if there's a turning point. So let's start with some polynomials that you're familiar with from Algebra 1 and Algebra 2. In Algebra 1, we looked at linear functions. And when you have linear functions, you have lines that either go up from left to right, or it goes down from left to right. So linear functions have the shape of a line. And let's think about what determines whether my line goes up from left to right or goes down from left to right. You might say slope, right? So just note that the slope is actually the leading coefficient of our linear equation. And then so in Algebra 2, we looked at quadratics, which has, we know, a U shape. And so when you have a quadratic, when you graph it, you either have a U that opens up or you have a U that opens down. And again, think about how do we know whether it opens up or down? We look at the A value, which also happens to be the leading coefficient. So in both cases, the leading coefficient in the line and the parabola tells me whether it opens up or down. For the line, it tells me whether my line is going to go up from left to right or go down from left to right. Cubics, that would be x cubed, as you remember from your function dance video when we looked at parent functions. Cubics has a sideways S shape, so they are S-shaped. And you could have a cubic that goes like this, or a cubic that goes like this. And if you can guess whether it goes up from left to right or whether it goes down from left to right, that is also determined by the leading coefficient, whether that's positive or negative, just like the line. And then finally, we haven't seen quartic functions yet, but quartic functions are y equals x to the fourth power, and they are generally W-shaped. So you could have a W, some type of W that opens up, or you could have some type of W that opens down. And again, whether it opens up or down, that is determined by the leading coefficient, just like the quadratic equation. The A value determine whether it opens up or down. The other thing that I want you guys to note is the number of turning points that each type of function has. So if we look at the line, where you have the equation is y equals, it could be x to the first power, right? Does not have any turning point, either goes up and never comes back down, or goes down, never comes back up. But when you have a quadratic, y equals x squared, you have one turning point, and that turning point is our vertex. And then when you have the cubic, when we have y equals x cubed plus 2x, etc. You have two turning points, or at most two turning points. And then finally, when you have the quartic, y equals x to the fourth plus other terms, you can have up to 3 turning points. Here, here, and here. It turns 3 times. So if you can make the observation, the most number of turning points that a polynomial function can have is always 1 less than its degree. So for a quadratic, it always turns once at the vertex. And for a cubic, it can have up to 2 turning points. It won't necessarily always turn twice, but it can turn up to 2 times. And then for the quartic, it has up to 3 turning points, right? And then the other thing that I want you guys to note is see if you can see a relationship between the graphs of the linear, quadratic, cubic, and quartic function by comparing its end behavior, meaning what happens to my graph as it moves to the left side, and what happens to my graph as it moves to the right side. Are there any similarities or differences between the linear and the cubic, or the quadratic and the quartic? Some of you might be able to see that for my linear and cubic, when the degree of my polynomial is odd, these are my odd polynomials, x to the first power, x to the third power. For our odd degree polynomials, the end behavior are opposites, right? One side goes down and one side goes up. And then for the quadratic and the quartic, which has even degrees, y to the second and y to the fourth, you're going to notice that on the left and on the right, they both point the same way. They either both go up or they both go down. So that's a relationship that is true for all odd and even polynomials. All odd degree polynomials have opposite end behaviors. One side points down and one side points up. And all even degree polynomials have the same end behavior. They either both point up or they both point down. So without showing you what it looks like, can you guess what a quintic function would look like? That would be y equals x to the fifth power plus 3x to the fourth plus etc. Okay, so the degree is 5 because that is the term with the highest degree. A quintic polynomial, if we use the pattern that we observed, can have at most 4 turning points. Because the degree is 5, it can turn at most 4 times. And because it's an odd degree polynomial, the end behavior is going to be opposite. So if I start on the left and try to sketch out what a graph looks like, I could either start by going down, that doesn't matter, or I could start by going up. So I'm going to turn once, twice, 3 times, 4 times, and that's it. I can have at most 4 turning points, right? So one example of what a quintic polynomial could look like would be this, with at most 4 turning points. So just a recap of end behaviors. Because we know that polynomials continue forever on both sides, we can figure out based on a few characteristics whether they rise or fall to the left and to the right, describing what we call their end behavior. So as we mentioned earlier, odd degree polynomial functions have opposite end behaviors. And you already know this because you are familiar with the linear function. y equals x to the first power, the line, is an odd degree polynomial. And for the line, the end behavior goes opposite ways. Right? So for example, if we look at the function f of x equals 5x plus 3, so basically y equals 5x plus 3, this is a line that goes up from left to right. If you were to graph it, y-intercept at 3, slope tells me I'm going to go up 5, right 1. Probably a more steeper line. Let me draw a steeper line. Okay, so How do we determine that my line goes up from left to right is I look at the leading coefficient and I see that it is positive. So if my leading coefficient is positive, okay, that means eventually my line is going to go up to the right, and because my degree is 1 and I know that's odd, I know that the end behavior is going to be different, so if it eventually goes up on the right, it must go down on the left, right? So if it's an odd degree polynomial, we know that it has opposite end behaviors. And if it has a positive leading coefficient, it tells me that eventually my graph is going to go up to the right, meaning that it must go down to the left on the left side of the graph, because it has to be opposite. And similarly, if your leading coefficient, or in this case for your line, your slope was negative, then you know that your line goes down. And so if the leading coefficient was negative, we know that my line is going to go down to the right. And it's going to go up to the left. Okay, so if we look at one more function, let's look at f of x equals negative x cubed plus 2x. Okay, so when I see this, although I don't know exactly what this graph looks like, I do know that it is odd degree. The degree is 3. We always take the degree of the term with the largest degree. So it's odd. I know that on the left side and on the right side, the end behavior is going to be opposites. And my leading coefficient is -1. And so because it's negative, I know that on the right side, it's going to go down. And on the left side, it's going to go up. Leading coefficient negative, meaning that eventually my graph is going to go down on the right, which means that on the left it must go up. Okay, and so x cubed is your sideways S shape, so it's going to look something like that. And so for even degree polynomials, I want you guys to think of the parabola. For the parabola, both arrows point in the same way, right? They either both point up or they both point down. So even degree polynomials have the same end behavior. And if the leading coefficient was positive, you would have a parabola that opens up. So the end behavior for the left and the right side is that they're both going to go up. So it's going to go up to the left and up to the right. And if the leading coefficient was negative, you have a parabola that opens down, and it would go down to the left and down to the right. And your parabola is y equals x squared, and that's why it's an even degree polynomial. So again, let's look at two examples. We'll start with f of x equals -2x squared minus 3. And then we will also look at f of x equals x to the 4th minus 2x squared. Okay, so looking at the first function, I see that the degree is even, meaning that the end behavior is going to be the same. And my leading coefficient is negative, meaning that they're both going to point down. So my graph is going to look something like this. And it's going to go down to the left and down to the right. And then for my second function, I see that, okay, x to the fourth, my degree is again even. That means it's going to point, both end behavior is going to be the same. And my leading coefficient is 1, it's positive. So that means they're both going to point up to the left and to the right. And x to the fourth is some type of w, so it's going to look something like that. So it's going to be up to the left and up to the right. Okay, so if I give you a function, even if you don't know what it looks like, if I give you a function like f of x equals negative 3 x to the 12th power, you see that the 12th power is even, so they're both going to point the same direction. And the leading coefficient is negative 3, so they're both going to point down. So you can describe, without knowing exactly what the graph looks like, you can still describe what happens as my graph approaches the left side and as my graph approaches the right side. Alright, so let's practice on sketching the graph of a polynomial by finding the zeros and knowing the left and right end behavior. So we've got f of x, or y, equals negative x cubed plus 4x. Let's start by finding the zeros, the x-intercepts, so we know that where my graph crosses the x-axis. So remember that zeros are really just x-intercepts, and to find the x-intercept, we make y 0. So I'm going to replace f of x with 0. 0 equals negative x cubed plus 4x. And to solve for x, we can solve by factoring. My GCF is negative x. If the leading coefficient is negative, we always factor out the negative. And I'm left with x squared minus 4. And then x squared minus 4 is a difference of 2 squares, so I can factor that out to x plus 2, x minus 2. So I've got 3 factors that multiply to give me 0. In order to make this equation true, one of these has to equal 0. So we know that x could be 0, x could be negative 2, or x could be positive 2 if we set each factor equal to 0 and solve for x. So that means I have an x-intercept at 0. I have an x-intercept at negative 2, and I have an x-intercept at positive 2. So when I draw my graph has to hit all 3 of these points, these zeros. And then in terms of the end behavior, I look at the degree. Okay, the degree is 3 because it's x cubed, and it is odd, which tells me that on the left and on the right side, the arrows are going to go opposite ways. And then we look at our leading coefficient. Our leading coefficient is negative 1. So because it's negative, I know that eventually on the right side, think of your line. Eventually on the right side, it's going to go down. So I know that it's going to go down on the right, which means that on the left side, it's got to go up. Okay, so for all odd degrees, I want you to think of the line. And for all even degrees, I want you to think of the parabola to help you make that relationship. And then if the degree is 3, how many turning points can it have? We know that it can have a maximum of 2 turning points. It can turn twice. Okay, so let's go ahead and sketch our graph. I'm just going to start up here. Cross my first x-intercept. Somewhere it's going to turn so it can come back up and hit my second x-intercept. And then again, somewhere here it's going to turn again so that I can come down and hit my third x-intercept. and goes back down. So we can see that on the left side it goes up, on the right side it goes down. And we don't really know here how far up, or here how far down it goes, but we're just making a sketch. Alright, so pause the video for a minute and go ahead and try the next two problems with your table group, and then you can skip forward in the video to check to see if you did it correctly, and if you did, you can move on, and if you didn't, you can rewind and watch how I did it. So graphing 3x cubed minus 15x squared plus 18x. First of all, we know that the degree is 3. Okay, and because it's odd, I know that my left and right end behavior is going to be opposites. So opposite end behavior. And because my leading coefficient is 3, and it is positive, that means eventually on the right side it's gonna go up. So if it's opposites, then that means on the left side it's gotta go down. Okay, so let's see where the zeros are, the x-intercepts. Zeros only refer to the x-intercepts. I'm going to make y equal to 0 and solve for x. So 0 equals 3x cubed minus 15x squared plus 18x. And I can factor out a 3x from every term. That's the GCF, and I'm left with x squared minus 5x plus 6. And then I can factor that quadratic further. X minus 6, x plus 1. Factors that multiply to give you 6 and add to give you negative 5. And then once I have it factored, I can use the zero product property to solve for x. 3 factors multiply to give me 0. In order for this to be true, one of them has to equal 0. So either 3x is 0, in which case x is 0, or x minus 6 is 0, in which case x is 6, or x plus 1 is 0, in which case x is negative 1. So these are the 3 values that would make y equal to 0. So those are my 3 x-intercepts. I have one at 0. I have one at 6. 1, 2, 3, 4, 5, 6. And I have one at negative 1. These are the 3 points that my graph has to hit. Okay, so let's go ahead and draw our graph. And because we know that the degree is 3, there is only at most 2 turning points. Remember, the maximum number of turning points has to be 1 less than the degree. So I know it's going to start somewhere down here. It's going to hit my first 0, and then it's going to turn around, hit my second 0, and then at some point it's going to turn again and hit my third 0 and goes up forever. So that's generally what your graph would look like. Let's try one more. So f of x equals negative 16 plus 10x minus x squared. The degree here is 2. This is not written in standard form. It's not written in order. So let's just rearrange it and put it in order. Negative x squared goes first, and then 10x is the next term, minus 16 is the constant. So the degree is 2. And because it's even, we know that it's going to have the same end behavior. They're either going to both point up on the left and on the right, or they're going to both point down. And then we look at the leading coefficient. The leading coefficient is a negative 1. So because the leading coefficient is negative, I know that they're both going to point down. So on the left it's going to point down, on the right it's going to point down. And so again, let's find the zeros, the x-intercepts, by making y equal to 0 and trying to solve for x. Okay, here we can, before we factor, we can divide out a -1 or factor out a -1, up to you. I'm going to divide every term by -1 just so I don't have a negative x. And I have 0 equals x squared minus 10x plus 16. And then we can try to factor. Factors of 16, that would add to give me -10. That would be -2 and -8. That would multiply, give me 16, and add to give me -10. Alright, and then once I have my two factors, we can use the zero product property to solve. Two factors multiply to give me 0. One of those has to equal 0, so either x minus 2 is 0, in which case x is 2, or x minus 8 is 0, in which case x is 8. And so my two x-intercepts, so my two zeros, are at 2 and 8. Right here. Okay. Alright. And then the number of turning points. Because my degree is 2, it can only have one turning point. It is a parabola that opens down. And so it's going to look something like this. Parabola that opens down on the left, and it doesn't have to be all the way here, although it can be, but as my graph moves toward the left side, it points down. So I'm going to start on the left and then go through my first intercept, and then my turning point comes back down and both arrows point down. So again, how do you know how far up this parabola is? This vertex is, we don't, we're just generally sketching it out. So your homework is the last page to your packet, where using the first part is looking at each function that is given and using the degree and the leading coefficient to determine what the end behaviors are. Whether it goes up on the left or goes down on the right, or it goes down on the left and goes down on the right. So look at the degree. If it's even, it's the same. If it's odd, it's different, it's opposite. And then look at the leading coefficient. If it's even, that tells you they're gonna both point down. Odd tells you they both point up. And then if it's positive, tells you that they both point up. And for odd degree polynomials, think of the line. If the leading coefficient is positive, it eventually goes up on the right, which means on the left it goes down. And if the leading coefficient is negative, it eventually goes down on the right, which means on the left it goes up. Okay, and then the last part is just matching the graphs to the equation that is given. Again, looking at the leading coefficient and looking at the degree to help you figure out which graph matches with what.